Okay, everybody. So part A is to prove that this sequence is monotone increasing. Okay, so first, for part A, I would just say that monotone increasing means that the x sub n, like the next term should always be bigger than or equal to the previous term. You could also just say that xn minus 1 is less than or equal to xn. There's so many different ways you could do this. Xn should be bigger than xn minus 1. Like, whatever way you do it is fine. Okay. Oh, and that should be, for all n. Okay, so how do we do that? Well, we just observe that this inequality here is true if and only if, well, let's just, okay, by the way, this should be x sub n. And so we're just going to plug in n plus 1 and n. 2n minus 3, 2n plus 3, 2 times n plus 1 minus 3, 2 times n plus 1 plus 3. Okay. And we're just going to keep going until we get something that is obviously true. And then the proof is done, because we just follow the if and only ifs back up to what we wanted to prove, which is that the sequence is monotone increasing. Okay, so let's continue. Maybe we'll simplify these things. So we'll have 2n plus 2 minus 3. We're going to have 2n plus 2 plus 3. And we'll leave these the same. And now, n is a natural number. In particular, it's not negative. So multiplying by 2n plus 3, if we multiply both sides by 2n plus 3, these will cancel. And this side will get a 2n plus 3. And so, anyway, I guess what I'm really trying to say is that this is true if and only if 2n minus 1 times 2n plus 3 is greater than or equal to 2n minus 3 times 2n plus 5. In other words, we cleared denominators. Now, you have to be careful with inequalities. If this was a negative number, then that would flip the inequality sign. But luckily, both of these are positive. Okay, let's just multiply out. So there'll be 4 terms greater than or equal to another 4 terms. Okay, and these will cancel. We can subtract 4n squared from both sides, and then simplify the rest. Minus 2 plus 6 is 4. Minus 6 plus 10 is 4. Wait, is that true? Oh, great. And then we can subtract 4n from both sides, and we'll get minus 3 greater than or equal to minus 15, which is obviously true, and so that is done with part A. So we proved this is true for all n because this is just true. And it didn't matter what n was. This will always work. Okay, let's do the next one. Show it is bounded. Show it is bounded. So in order to show something is bounded, we just need to show, prove that x sub n is always less than or equal to some number. Usually it may be called capital B. Because these are real numbers in this case. I guess really we could take the absolute value if we wanted to allow complex number sequences. But I mean, these are just real numbers, which are also complex numbers, but some positive number. Okay. So that would be bounded. This is bounded. Now, how do we prove it's bounded? Well, we have to do some experimentation. Maybe you can spot already a bound, but let's just see what x1 is. x1 is, no. x2 is, what's x2? 4 minus 3. x3 is 3 over 9. x4 is 5 over 11. Well, anyway, what we're hopefully spotting is that this number is less than or equal to 1. Okay, so 1 is the bound. And how are we going to prove that? Well, let's just show. Claim 1 is a bound. Okay, so let's look at 2n minus 3 and 2n plus 3. What I'm claiming is that this is always less than or equal to 1. And let's see, 2n minus 3 less than or equal to 2n plus 3. And cancel the two n's. And this is always true. So, and these are if and only if and only if. This one is true. So we're done. Okay, now find and prove its limit. What is its limit? Well, its limit, I think, even though these are pretty separate, I think it's actually going to go to 1. Just going to get closer and closer to 1. Maybe in calculus you might have said, well, 2 over 2 is 1. And we ignore the minus 3 and plus 3, because as n gets big, minus 3 plus 3 just won't make a big difference. Okay, so for example, x100 will be 200 minus 3 divided by 200 plus 3, which is very close to 1. And the thing is just increasing, so it's going up and up, but it's always less than or equal to 1. Because it's bounded by 1, it's less than or equal to 1. But it's increasing, and so it's probably going to go to 1. And that is the key. Find and prove its limit using convergence game. See, so we're going to claim that the x sub n go to 1. So let's start proof of this claim. Sometimes a claim is called a theorem. We need show that for all d there exists a capital N such that little n past capital N implies that, well, the x sub n are d close to 1. And this needs to hold for every single d. There should exist some capital N. So in other words, we need to find capital N for every d. Okay, well, let's investigate this. This is our goal, so let's calculate with it. What's x sub n? 2n minus 3 over 2n plus 3. And now let's rewrite. 1 is, the best way to do it is just to write it like this. That's a 1, so we're going to subtract that. And we need the absolute value less than d. And now now they have a common denominator, so we can subtract the numerators. 2n minus 2n minus 3 minus 3. But now a minus 6, when we take absolute value, becomes a 6. And the 2n plus 3 is positive, so we can just remove the absolute value and change the minus to a plus. Okay. And so this is true if and only if 6 divided by d is less than 2n plus 3. So now at this point we can say, dear reader, you must agree that we can find a capital N such that 6 over d is less than 2 times capital N plus 3. Okay. We could go this route, but let's just make it more explicit. Let's subtract 3 from both sides. And let's divide both sides by 2. Okay. Dear reader, you must agree that we can find a capital N such that 3 over d minus 3 halves is less than capital N. And this is true no matter what d was chosen. No matter what d they challenge us with, we can find a capital N such that this is true. Okay? But then, if little n is greater than capital N, that implies that little n is greater than capital N, which is greater than this thing, which is true. This inequality is true if and only if xn minus 1 is less than d. And that is the end of the proof. Okay. And this maybe is by star, and I'll call star these calculations. Okay. So now we've shown that this sequence is monotone increasing. It's bounded, it's always less than or equal to 1, but it's increasing. And so it actually converges, and we proved that it does converge to 1. Okay, can you do this yourself now? Try it with a blank sheet of paper. Blank. Here's a sheet of paper. How do I draw a sheet of paper? Maybe like this. This is more like parchment. Oh, that didn't make sense. Well, this is not math, but anyway, here's the sheet of paper. And now you can try the proof by yourself.